Hello, my name is Jeremy Seek. I'm a professor at Indiana University. And this video is going to be about proof techniques using the Deduce proof assistant. We're going to go over how to use switch to break your proof into cases based on a union data type. We'll also introduce a couple other handy sort of proof statements in Deduce. A version of replace that you can use on a given instead of the goal, and similarly a version of expand that you can use on a given instead of the goal. Okay. All right, so let's dive in. Here we've got a union that we saw in an earlier episode. So here is a linked list of integers, of unsigned integers. Each part of the list is either a node, in which case it has an integer inside the node, and then a pointer to the next node. And then at the very end, there's going to be an empty. Okay. And then we've seen this recursive function before. This is the length function, or len for short. And of course, the length of an empty list, it has no elements in it, so this length is 0. The length of a node is going to be 1 plus the rest of the list. Okay, so we've seen these things before. Now we're going to dive into proving a theorem here. That's going to be an example of using this switch statement. Okay, so suppose we have, any list of unsigned integers. Okay, let's call it xs. Okay, as our variable xs. And here's the theorem. If the length of xs is 0, then that list better be empty, right? The only way for that length to be 0 is if it's empty. Okay, so this should be true. Pretty obvious. It's good. We can't prove false things. We can only prove true things. So let's go ahead and give this a shot. All right, so we kick this off. Deduce is telling us we need an arbitrary to prove this all, so we'll go ahead and do that. As usual. Then the next thing, now we're trying to prove this if-then statement. Okay, so as usual, we're going to assume the premise of the if, right? We're going to assume length of xs equals 0. And then now we need to prove the conclusion, right? The xs is equal to empty, right? So that's our, Deduce tells us that's our current goal. And Deduce's advice is not quite so specific this time. It's like, well, you need to prove an equality. Maybe you want to use expand or replace or equations. But at this point, Deduce doesn't really have specific advice for us. And furthermore, we've got a little bit of a problem here. Okay, so we know that the length of xs is 0, right? That's this premise that we know about. But, I'm keeping this other window open here with the definitions of length. If we look at the length here, if we want to know whether the length is 0 or 1 plus whatever, we need to know if the argument to length is empty or a node. And over here, we don't know that. We just have this, it could be anything. It could be a node, could be empty. It's just this arbitrary list, xs. Okay, so this is where switch comes in. Switch says, hey, there's only two possibilities for xs. If we look here at the definition of this union, there's just two clauses here. And so switch will say, hey, let's reason about each clause. Right, so we're going to break our proof down into cases, and we're going to have to consider each case, right? Each possibility. Okay, so this is what a switch statement looks like in Deduce, or a switch statement looks like in Deduce. It's a switch proof statement. There's also switch term statements that you can put inside of function definitions. This is for when you're doing a proof, though. Okay, so now you can see that we have these two cases to prove. Okay, and the first one will be, what happens if XS is empty? Okay. Actually, maybe up here, I'm going to go ahead and I want to make this proof a little bit more readable. So I'm gonna document what the goal was. Actually, let's not worry about that. Let's just dive into here. Okay, so our goal was XS equals empty. Okay, and now our goal has all of a sudden magically transformed into just true. So what happened there? Okay, well, let's see what happened to this goal, right? So our goal was XS equals empty, but because we're inside this case where XS is empty, Deduce transformed our goal into that equation, okay? And then furthermore, whenever Deduce sees an equation with exactly the same syntactic entities on both sides, it just turns that into true, okay? So now we can understand why our goal down here is just true. So we can just prove this with a period, right? It's obviously, there's nothing to be done there. Okay, now let's look at our second case here. Okay, this at first might seem a little bit troubling. Our goal has turned into just false. Okay, so let's first see how that happened, okay? So again, our goal was XS equals empty, but now we know that XS is equal to this node here. Okay. Maybe one little note about these new variables X and XS prime. Think of these as, these are pattern variables that are being attached to whatever was inside the node that XS is, okay? So it gives us a way of referring to the pieces of XS. Right, we know it's a node, so we know it has these two pieces underneath. Okay, so Deduce transforms our goal into this equation, but now this equation is sort of interesting. We've got, we've got this union that could be empty or a node. We've got node on one side and empty on the other. There's no way that's true. Okay, Deduce always makes, Deduce knows that when you use two different constructors for a union, they're different, okay? So Deduce reduces that equation to just false. Okay, so that explains why our current goal is false. But now it's like, wait a minute, it's impossible. Like, normally it's impossible to prove false. Okay, so what on earth is going on here? Okay, well, usually when you see that you need to prove false, what you should be thinking to yourself is, maybe there's a contradiction in the things I already know, okay, in my givens down here. Okay, so, and maybe we just need to sort of shake our givens a little bit to, to sort of make that contradiction apparent to Deduce, okay? Deduce is not gonna sort of do a lot of thinking about it. We gotta put the pieces together to sort of show to Deduce that there's really a contradiction, okay? So one sort of simple step we could take is we're looking at this premise that's about XS, but now we know that XS is actually a node. So it'd be kind of nice to have the XS down here turned into node, okay? And so this is where we're going to have this, we're going to use this new feature called replace in, okay? So we're going to do a little bit of forward reasoning here, and we want to know that length, we're going to try to prove that length of node XS prime is equal to 0. Right, because we're basically saying, we want to use this premise, but we want to update it with this other premise. Okay. Actually, you know what? We're gonna need to refer to this other given here, and that was actually that came into existence as part of this case statement. So the way we can actually give that a name is we can go ahead and do that. We can give it a name, and then now if we look at down here, we see excess node is the name for this equation. Okay. All right. So now what we want to do is we want to do a replace, where we're using this equation, the excess node equation, to replace the excess inside of premise. So here we say in premise. Okay. And the result of that will be len node equals 0. Okay, let's see if Deduce is happy with that. Indeed it is. It passes on by that have. And now we still need to prove false. But okay, thanks to that have, we now have a new given here, which is the length of this node is equal to 0. Okay. All right, well then the next step we need to take is that, okay, well now we can use the definition of length, right? Looking back over here, if we have length of a node, that's going to be 1 plus the length of the rest, right? So let's go ahead and do that. Actually, now I'm gonna actually not even write down the formula we're trying to prove, because maybe we can get Deduce to tell us what the formula needs to be. Okay, so we want to expand the length function in len 0. Okay, this is interesting. So that worked, and now Deduce is telling us that the formula that we get by expanding length in len 0 is actually the formula false. Okay, so we can put false here, and Deduce would be happy with that. Okay, let's think about why that happened. Okay, so when we expanded len here, okay, we're using this formula over here. So what that turned into, let's go ahead and see what this formula turned into, right? It turned into 1 plus len of xs, okay? And so here we've got a 1 on the left plus something, and it's an unsigned integer, so it has to be, this has to be 0 or greater. And then over here we have 0, right? There's no way this is true, right? And so Deduce can recognize that, and it goes ahead and it actually just converts that automatically to false. Okay, so the fact that we have a 1 plus something being equal to 0, Deduce turns that into false. Okay, false is what we were actually trying to, that's what we're trying to prove. That's our goal, right? So we could just actually change this have into a conclude. And we're done. Okay, so let's kind of recap this proof. We were trying to prove a for all statement about these lists of unsigned integers, right? And this is a union type. And then we had this premise about the length, but we couldn't apply the definition of that length function unless we know whether the XS variable is empty or a node. We didn't know which one it is. Well, we could then use switch to sort of break this down into cases. What if it's empty? Do the proof. What if it's a node? Do the proof. If we can actually do the proof for both cases, we've covered all possibilities, and indeed, this is a valid proof for any unsigned integer list. Okay? So that was how to use switch. Along the way, we learned how to use replace in to sort of apply an equation to change one of our givens. And we also learned how to use expand in to expand a function definition, again, in one of the things that we've previously already proved. In this case, it was the len 0 formula. Okay. So next up, we're going to be learning a super powerful technique, one sort of more powerful than the switch here, which is called induction. We'll learn how to do induction on lists. Okay, so that'll be our next video. I'll see you later.